All right, we've just learned what an antiderivative is, and so I want to get practice figuring out some antiderivatives of functions. And we will eventually be getting to different rules with antiderivatives, but I want to just try and think logically and see if we can figure out what these antiderivatives are based off of our knowledge of derivatives. So I'm going to give us several functions, and for each of these functions, I want us to find the antiderivative. So we're going to get some practice here. The first example I want to look at is f of x equals sine of x. So we want to find the antiderivative of sine. So we want to know what function, capital F of x, gives us a derivative of sine. Some of you know the answer, but if you don't, we can think a little bit. We know the derivative of sine is cosine, but we want to go in the opposite direction. The derivative of cosine is negative sine, so that's almost there. But if it was cosine, the derivative would be negative sine, but we need it to be positive sine. So what we can do is we can take the opposite of this, and so the derivative of cosine is negative sine, but then that extra negative ends up making it positive. So an antiderivative of sine of x is negative cosine of x, but the general antiderivative is going to be negative cosine of x plus our constant capital C. So we've got negative cosine of x plus c. Let's look at another one. Let's look at f of x equals cosine of x. We need a function whose derivative is cosine, and I think you know that one. The derivative of sine is cosine, so that's going to be sine of x plus a constant. All right, we're doing well. Let's continue. Let's look at a curious one, f of x equals 1 over x. Can you think of a function whose derivative is 1 over x? We have seen this already. You might remember that the derivative of ln of x equals 1 over x. So we're going to write ln of x plus a constant. But there's a little bit more going on with this problem than what we have so far. If we think of the domain of 1 over x as a function, the domain is all real numbers except 0, right? The positives and the negatives. But ln of x is only defined on the positives. We can't take the logarithm of a negative number. But you might remember the day that we looked at the derivatives of logarithms, and we got 1 over x, we talked about the domain issue here, and we said that the derivative of ln of the absolute value of x was equal to 1 over x. We actually looked at this as a piecewise defined function. We split it up into the positive x's and the negative x's and whatnot. And we saw that regardless, when we had this absolute value, we got a derivative of 1 over x. So to make sure that we include the whole domain of this original function, when we take the antiderivative of 1 over x, we're going to write ln of the absolute value of x plus a constant. This is a really big one. I'm going to circle it. I mean, it's not huge, but it's one where we've got to be careful so that we have the whole domain. If we don't have this absolute value, then we've only found the antiderivative for one side of this domain, one side of this function. We need the absolute value there so that we've got the whole thing. All right? I've got one more that I want to look at here. This is an interesting one. F of x equals x to the n. So a generic power of n, except we're going to say n does not equal -1, simply because when n is -1, this becomes x to the negative first, which is 1 over x, which we've already looked at. This is kind of a special case, but if the exponent is anything else, then we are going to have a different rule that we use. Now we know that when we take the derivative of a power function, the result ends up having a degree that's one less. So we might think when we take the antiderivative, we get a degree that's one more. So we might think the antiderivative, capital F of x, equals x to the n plus 1, plus a constant. And that is almost true, but we're going to have to make a little bit of an adjustment. If we differentiate x to the n plus 1, that's going to pull out the n plus 1 out front and then decrease 1 from the exponent. So if we were to differentiate this, we would get n plus 1 times x to the n, because we would take the exponent out front, and then we would decrease the power by 1, gets rid of the 1, and we turn into n. But this is not what we want as the derivative. We just want it to be x to the n. We don't want this n plus 1 out front. So to get rid of that constant multiplier of n plus 1, we need to divide this by n plus 1, because then that's going to divide the derivative by n plus 1, and those are going to cancel, giving us the derivative that we want. So here, this is kind of a power rule for antiderivatives. If we're taking the antiderivative of x to a power, so long as that power is not negative 1, the answer is going to be x to the n plus 1. So we raise the exponent by 1, but then we have to divide by that new exponent. So we've got capital F of x equals x to the n plus 1 over n plus 1 plus a constant. So these are some examples of antiderivatives of functions. There are more examples in the example video. You should go through them. You should try them yourself first. See if you can use some logic to figure out what the antiderivative is, and then check the video afterwards to make sure that you've got it right. The more practice we get with these antiderivatives, the more comfortable we get with it, the more easy things are going to be moving forward.